The last few pages in chapter 18 are about complex ions. There is going to be a much more thorough discussion of these kinds of ions in chapter 22. Chapter 22, however, is not covered that extensively on the AP exam, just so you know. Another interesting thing about complex ions is that you've had them before, but we always just talked about the complex ions when we had metals surrounded by water. For example, copper sulfate pentahydrate, where we have the .5H2O, that's a complex ion. This section takes it to the next level, where the water molecules are actually embedded in the formula, as opposed to attached at the end of the formula with the dot. For example, here is a complex ion where you have 6 water molecules that have hydrated or surrounded the nickel-2 ion. This means that polyatomic ions, as well as small molecules, can surround a metal ion, creating the complex ion. Naming these complex ions can get very complicated, but not something that you will need to know for the AP exam. You should recognize, however, when you get a complex ion. Another point I'd like to make is, up to this point, we have talked about the following kinds of equilibrium constants. There was the KSP for weakly soluble salts, the Ka for weak acids, the Kb for weak bases, and the Kw as the equilibrium constant for the dissociation of water. Now we add a fifth one called Kf, which is the equilibrium constant for the formation of a complex ion. These complex ions, where molecules or polyatomic ions surround a metal ion, are called ligands, from a Latin word meaning to connect or attach to or grab hold of. Think of a ligament in your muscular system. Many organic molecules form these complex ions, and that's why we often use organic compounds to try to remove metal ions from environments. This is one of the ways that we preserve things like mayonnaise and salad dressings, is by having a compound that will complex with metals. The reason we don't like metals in foodstuffs such as this is that they catalyze or expedite the decomposition or rotting of the organic food. If you look down here towards the bottom, you can see how the copper ion will successively connect with one ammonia, and then a second ammonia, then a third ammonia, and then a fourth ammonia. So that last complex ion, this one right here, would be called the tetraamine copper-2 ion. Tetra means 4, and amine is a prefix that usually refers to the ammonia molecule. You'll also notice that the equilibrium constants for their formation have positive exponents instead of negative. So these equilibrium reactions go pretty far to the right, which means these complex ions preferentially form. And in the process of copper gaining 1, then 2, then 3, then 4 ammonias, the overall formation constant would be multiplying all 4 of these individual formation constants together, and you get a huge number, 2.1 times 10 to the 23rd. Here is an example problem. What is the concentration of the copper 2 ion in a solution prepared by adding 0.00100 moles of copper 2 nitrate to 1 liter of 1.5 molar ammonia? Now, once again, we're going to follow the strategy that I've encouraged you to adopt, and that is the first thing you do is write the equation. And the equation is right on top of the ice chart, down towards the bottom, in dark print, where you have the tetraamine copper 2 ion in equilibrium with the copper 2 ion and 4 ammonias. Once you write the equation, then writing the equilibrium expression is simply writing the products over the reactants. Now, the ice chart, when we go to fill it in, you'll notice that we are beginning with a 0.00100 molar solution of my complex ion, and we're also beginning with a 1.50 molar solution of ammonia. Now, a little bit of that ammonia is actually tied up in the tetraamine copper complex ion. And the reason where we get that 0.00400 from is it's 4 times the 0.00100 due to the stoichiometry. Now, if that doesn't make a whole lot of sense, the nice thing is that the number 0.00400 is very small compared to 1.50 and is not going to make too much of a difference if you forget to do it in a calculation. Then when you add up your first 2 rows to get your equilibrium molarities, once again subtracting X, which is the number of tetraamine copper 2 complex ions that you have in solution that have dissociated, that number X is very, very small. Even 4X would be very, very small. Consequently, you end up at the very bottom of the ice chart with your equilibrium molarity of your complex ion as being 0.00100 molar, approximately, to 3 sig digs. And your molarity of your ammonia is approximately 1.50 to 3 significant digits, because that minus 0.00400 just barely doesn't show up. If it got a little bit higher, it would show up. Then you can plug your numbers in at the bottom. And of course, you want to pay attention to the fact that when you write the equation as you see it above the ice chart for the dissociation of the complex ion, that is the opposite of the formation of the complex ion. So the formation of the complex ion is the Kf, but you want the dissociation, which is the reciprocal, the reverse of the reaction, so the reciprocal of the formation ion constant. That is a common mistake that is made. So again, when you're forming your complex ion, you use the formation constant. When you're taking the complex ion apart, you use the reciprocal of the formation ion constant. Now, the solubility of these complex ions is taken up in this very last section. Silver chloride, as you should know, is one of the few chlorides that is really insoluble in water. It's even insoluble in strong acid, but it actually will dissolve in a base if you have enough base. And that would create the diamine silver 1 complex ion. Diamine means you have 2 ammonias in the formula. And so you can see the equation at the bottom that if you combine silver chloride with ammonia in a 1:2 ratio, you get your complex ion, and your chloride is, in a sense, your spectator ion if you wanted to cancel it out in water. So your silver chloride would hardly dissolve at all in water. But then when you start adding the ammonia, you begin to drive the reaction to the right. And as you drive the reaction to the right, you remove the silver ions from the solution because you're making the complex ion. So the degree to which the silver chloride separates into silver ions and chloride ions is not much. You can see that by the KSP of 1.8 times 10 to the minus 10th. But then in the second equation, if you take those silver ions if you take those silver ions above there and combine them with ammonias, that reaction goes pretty far to the right, 1.1 times 10 to the 7th, or in other words, about 10 million. We call this example of combining these two steps coupling, or putting the two equilibria together. And one of the equilibria is not product favored, 10 to the negative 10th, and the other is product favored, 10 to the 7th. So when we multiply these two K values together to get the overall or net K value down here, you can see that it's still less than 1, but it's pretty substantial in that you've increased it by a factor of almost 10 million, from 10 to the minus 10th to 10 to the minus 3rd. And that means your silver chloride becomes more soluble in ammonia than in pure water. Other things will do this as well. Here you have the chloride ion, and that's creating a rather unusual complex there, AgCl2 with a minus charge, or the thiosulfate ion, S2O3 2 minus, or the cyanide ion, Cn minus. Each one of those would be the anion of, say, a sodium or a potassium compound. And as a result, you get a constant, equilibrium constant of formation that is substantially bigger than 1, which means this reaction goes to the right. Now, these pictures are kind of interesting in that it demonstrates what we call a progressive precipitation. You can precipitate out the silver chloride. Then if you add some ammonia, you end up dissolving the silver chloride and precipitating out your diamine silver 1 ion. Then in the third picture, if you add some sodium bromide, now you precipitate out something that is even less soluble than the previous two, silver bromide. Then if you add some sodium thiosulfate, you get the fourth picture where you produce the least soluble of all, the dithiosulfate silver 3 minus complex. And so you become successfully less and less soluble as you continue to add to the same beaker a different soluble salt, sodium bromide and then sodium thiosulfate. The last example in this section on complex ions shows what happens when we add a soluble thiosulfate like sodium or potassium thiosulfate to a solution of silver bromide. Silver bromide is marginally soluble, 10 to the minus 13, as you can see by the first equilibrium equation. But if we take those silvers and now add some sodium or potassium thiosulfate, those silvers will combine with the thiosulfates to create this complex ion, which has a formation constant that is very large, 10 to the 13th. Consequently, adding sodium or potassium thiosulfate to your silver bromide drives the reaction to the right. You multiply the two constants together to get your net constant, and you get a value that's over 1, not big time, but it's 15 is certainly over 1, driving it to the right, improving the solubility of the silver. And again, you have a review and check if you want it.